Today I'll speak about work in progress that I'm doing with two postdocs at Juin, Marcelo de Martino and Roy Oste. If I describe the research we're doing, we're studying an algebra. And it's an algebra of generalized symmetries for certain generalized Dirac operators. There's a lot of generalized. I will go over it. Why is it? And in particular, we're not so general, so we concentrate in ourselves for D-wall deformation. So that means it's an algebra that I'm studying in my PhD. What I was saying? Oh yeah. So this algebra we've studied we have some general results on it. We have a presentation, generator, and relation. But we want to study its representation theory, and for that we only have specific groups in mind. In this talk, I'll concentrate in two diagonal groups. So I'm deforming this Dirac operator by reflection groups, and I'm focusing on diagonal case. We are doing it for more diagonal, but let's just focus on two because we have nice images. What I want to use and what are those images mean is, that's a bit shaky. The images mean a certain construction of the representation using a structure of a sub-algebra. It will become clear at the end, or at least I hope. So small outline, we will skip it, and we will go straight to the preliminaries. So I mentioned that what we are deforming is deforming in base of reflection groups. So we need to introduce some root systems. Most of you probably know root systems, but they are beautiful, so we can spend a bit of more time to look. The only thing I want to say, and that's the reason I put all crystallographic root system, is that we are considering general root systems, so also non-crystallographic root systems. In particular, in 2D, you have an infinite family of diagonal root systems. Root systems are a bundle of vectors in a certain Euclidean space with the binary forms that have a lot of symmetries. In particular, if you look at our reflection along hyperplane, your root system are all the vectors that they all stay invariant. They all are inside this root system. So if you reflect according to one root, you will go to another root. And then you can take your reflection group to be the group generated by all the reflections along the different hyperplanes. For example, for the A2 root system, you get S3 or D6 because I like diagonal. The other preliminaries we will need because we are considering a certain Dirac operator, so we will need a Clifford algebra. So if we have a vector space within binary form, non-degenerate symmetric form, the Clifford algebra, I will take all the elements of V and I add the anti-commutation relation, just that it's the anti-commute up to this, then the anti-commute if they are orthogonal to each other, and if not, if they get weighted by the binary form. So if you have an orthogonal basis in RD, then your Clifford algebra with RD anti-commuting variable ej to k, and they anti-commute to each other and they square to 1. We're already ready to go to the algebra of symmetries. To go for the algebra of symmetries, we will first put the context. So this is the big scary slide of rational Cherednik algebra. So my algebra of symmetry lives inside a tensor product of a rational Cherednik algebra and a Clifford algebra. Rational Cherednik algebra, we have multiple presentations for it. This one I'm presenting is you take your V, your Archimedean field, you take your dual space V according to your bilinear form, and you have reflection groups. So you take the group algebra of W, the reflection group W, and you have a certain function, a certain W invariant parameter function kappa that goes from the root system to C. You do take a tensor product on V and V star, you smash product with the group algebra, and you quotient with a lot of the relation. So you want the elements of V will commute with each other, the elements of V star will commute with each other, and the commutation relation between elements of V and V star is given by this this sum over the weighted elements of the root system. Maybe a small example in Z2. If you have just Z2 and your reflection group is Z2, you are on R, then you can have a generator represent the generator in relation. You have only 3 elements, X, Xi, and sigma. Sigma is the reflection. So we have sigma squares. Sigma X is minus x sigma, sigma psi is minus psi sigma, and they commute up to 1 plus 2 kappa. They were introduced by Ettinghoff and Ginsburg in the early 2000s. There's another way to think of the rational Cherednik algebra that is maybe more simple, certainly in my opinion, and this is by Dunkl derivatives. And it will be a bit clear. The Dunkl derivative is a deformation of derivatives using root system. So maybe you start seeing a bit the same thing. So you have your root system, you have a positive roots, you have your groups, and again, kappa. I take it on the real, it will be clear later. Why take it on the real is just a restriction on parameters. So your Dunkl derivative has a normal derivative and have a part as a sum on reflection and weighted by the kappas by the parameter function. So if you are in A1 in R, again, your reflection is simply sending x to minus x, and the Dunkl derivative on function is normal derivative plus fx minus f minus x over x. The main property of Dunkl derivatives that they commute, so they are almost behave as well as you want for the generation of a Dunkl derivative. But furthermore, to make a link with the rational Cherednik algebra, you can see the rational Cherednik algebra if you take a representation acting on polynomial space. You get what we call the Dunkl representation. It's a faithful representation. So in a sense, you could define your rational Cherednik algebra as using the Dunkl derivative and polynomial. To be a bit more clearer, so you see I already said that I wanted, 2 slides. Okay, so in this presentation, you get a Y algebra, so you have an algebra of x's and derivatives, but then you exchange your derivatives for Dunkl derivatives, and you will get the same relation that we had to define the rational Cherednik algebra. So in this talk, this is the setting we will do. We will view our rational Cherednik algebra as Dunkl representation. I said I was interested in the Dirac operator. I want to study an algebra that is the centralizer of a certain realization. So the main part of the rational Cherednik algebra is that they admit a SL2 triple inside. So elements that are this is their norm square. This can be seen if you change the P for eta. Sorry for the small typo here. Change the P for eta. This can be seen as almost as a Laplacian, and you have your degree element H. So they form SL2 triple. They respect the SL2 relation. HE is E, HF is minus F, EF is H, with maybe some minus, always missing it up. Because we are tensoring with Clifford, we also have least algebra OSP1 realization inside this algebra given by vector variable and generalized Dirac operator. So they are all generator of our OSP1 realization. What we are studying is algebra of symmetries. We are studying our algebra S VW kappa to be the centralizer, the super centralizer, the centralizer of this OSP1 realization. My supervisor, Hendrik de Bie and Joris van der Jeugd, with their student Roy Oste, made explicitly gave generator and relation for this algebra, and we want to study the representation. Okay, in this algebra, first thing first, because we are tensoring with the Clifford, the group appears, but it's not the group. We get the double covering of the group. So if you get a double covering of your orthogonal, you go back to the covering W tilde of W, and its elements will anti-commute with X bar and D bar. So thus they are in the algebra. For notation, I will put tilde on the reflections. You know that they are in the double covering, and I will keep sigma for the first dihedral and tau for the second dihedral. Just a bit of notation for further. Okay, just a bit of delay. I must be patient. Okay, so a result that Roy got lately, and that will motivate why we are studying this 4D case, is that the algebra is generated by the group algebra of W tilde and certain elements OXY and OXYZ that depends multilinearly on the elements of your Euclidean space V. Furthermore, in this algebra S, if you only consider the OIJ that are for the canonical unit vector, you get the deformation of the algebra SOD. So this deformation, what I mean is, by deformation, I mean if you look in our algebra S and you only look at those elements, you can get SOD plus a certain term, and this term goes to 0 if your deformation is 0. So if kappa is 0, if your group is trivial, this deformation goes to 0 and you get back this SOD inside the symmetry algebra. This is what I wanted to say about this algebra. Now, what has our goal is
those with 3 indices?
Those with 3 indices,
X, Y, Z.
they have also relations that are bigger, but I don't know if they deform something else. We know the relation. They are just taking all this. So the main goal of our is to study the representation theory. What we know, so there's not a lot of cases that have been done. There's one general cases for Z2D by Hendrik de Bie, Vincent Genet, and Luc Vinet, 2017. That is the higher rank finite algebra or finite algebra for rank 3. Hendrik de Bie, Roy Oster, and Werder Young have done when the group is S3 in O3 and gave an explicit presentation of our finite-dimensional irreducible representation. And we've done lately also still in dimension 3 all diagonal groups with the Z2 part, and gave again our finite-dimensional irreducible representation. This presentation, we want to stack multi-diagonals to get another general case. And in the presentation, we will focus on what I mean by diagonal deformations. I clicked 2 times, so it may be dangerous. I mean, my group is the 2 diagonals. I will switch back to an isotropic basis because diagonal interact nicely with the conjugation and the conjugate and the complex variables. My notation, I will spend OAB plus minus, or OZA and ZB, where ZA and ZB are above. And for the rest, the same. You have all choices of A and B and all choices of plus and minus. There's some special elements that I will use that only works for the diagonals, and that is why this diagonal case is interesting. If I have HA, which is OA plus A minus over 2, HB, OB plus B minus, what I have is that those HA, HB commute with each other, and the reflections for the first diagonals will anti-commute with the first HA and commute with the second, and similarly for the reflection of the second diagonals. Why is this interesting? Why is this? What can this say in the representation theory? Because of the following classical picture that we have. So if you only look at this deformation of SO4 that we add in our algebra, there's this exceptional homomorphism in SO4 splitting into SL2. And so you have a weight theory of the 2 SL2, and they will split. So representation will typically split into 2 of those rectangles. But you can navigate through weights using those O's, using the OAB or plus minus. We wanted to do something similar. However, we cannot using only the O's because everything gets sent. Try to generalize. We still have that the HA are diagonals. There's also central elements, O central, that will give the color. So in the last slide, we had 2 colors, and this is distinguished, but we still have central elements that can diagonal elements that can distinguish the 2 parts. It's the approximatively the square root of the Casimir. I can say the different. Well, the OABs are not what we want. They don't respect the weight space, and representation are irreducible this time for our algebra. I skipped the slide, I think. So what we define to cover this, define other operators. It's nothing so magical. They are the M's, and the M are simply I anti-commute 2 times with HA and HB. This way I get rid of certain unwanted, and they have ladder operator relations akin to the one of the classical picture. So in those, if now I'm navigating in the weight space, say I suppose my representation as a weight theory, I can navigate through the weights using my M's, and I get this picture with the only difference that I cannot cross the relation of the algebra I want. you can, since we are in 4D, we also have the tree index, and we can divide other operators, LA plus, LB plus minus, and that also generates some ladder operator relation. The nice thing with those M's, those L's, and the O central HAHB is that we have a triangular subalgebra. So we have a subalgebra T at the associative subalgebra generated by all those M's, all the M's, all the L's, W tilde, and 0. W tilde 0, what is it? It's the reflection in W tilde that commutes with HA. So typically, there's a reflection of the form sigma 1, sigma 2, tilde, and tau 1, tau 2, tilde. And then our triangular algebra, also triangular subalgebra, as by the name, a triangular structure with the T0 being the from the three weights O central HAH smash product with the. How can we use this and why is this particular? The reason it's useful for us is because we have a lot of factorization that we can do on the level of the algebra for this element. We can factorize LA and M's, so we can parameterize finite-dimensional representation in S. And the idea is we will restrict from S to T, find a label for the representation. And an important lemma that we would use is that for generic kappas, the weight space are one-dimensional. So now we are ready to go into the constructing the pictures, which would be the apex of the talk. So we have this over T. We can divide our representation to have an eigenbasis for O central, HA and HB. So the color will be O central and HA, HB will be in the next. We'll be able then to navigate through the weight space using M's, L's, and reflections. What it's looked like, I first start, you give me a finite-dimensional irreducible representation. I don't know anything about it, but I know that there's an IS weight. Or I can also do it the other way. You give me some data, and I give you the IS weight. Give me the IS weight. I navigate with it with the M's, then I cannot. Then I go to the second to IS weight with the L's, and I navigate with the M's. So I have ladder operators until I cannot. Then what we prove is that, well, you're doing this, you have now navigated with all the ladder operators, all the L and the M's. Finish this representation using two times. Using the full algebra by multiplying by the group, because normal in the triangular structure you don't have the full groups, you only have a subgroup. And then when you go to the full group, you get this full picture and you visited all the weights. Since all the weights are one-dimensional, and since you started with an IS weight, you visited them all. And you now have a representation, a description of the representation. This description could also have been done differently a bit. I will present a picture. It's a small internote. You could also have navigated with everything with the L's and the M's, went through all the weight space and get more relation. This is what we do to prove things. But when you've done this, you can show that you only need the picture. I thought there was another slide. But why are the factorization important? I realized it was clearer when I made it, but let's go. You start with an IS weight. Since you start with an IS weight, what it says to you, you have some condition. It's an IS weight, so we cannot. It's an IS weight in A, and an IS weight. Let's see. My IS weight, my partial orders on weight, or my order on weight. I want the maximal A and the maximal then B. Okay, clear? Since it's an IS weight there, I cannot be higher in A, and I cannot be higher in B. Thus, those two give me a factorization. Using the big factorization I presented, give me 0. Likewise, I cannot be higher with M. I cannot go because of the IS weight, and again, I get another factorization. Since it's finite dimensional, if I apply subsequently all M A minus B plus, I apply them a certain number of times, then I cannot apply, if I apply one other, I get to 0. And I again have those factorization that I presented before. Work on those factorization, you can extract the information of the label. So the color gives you the central weight. And finally, the only thing you need is when you induce to the full representation, you act with W tilde. So you look at what is the action of W tilde, or maybe less imageful, less colorful, but more precise. So if K is generic, that any finite-dimensional representation, previous representation of my symmetric algebra as a label. So sigma, the lambda A, lambda B, big lambda, and U, where my lambda A, lambda B are my highest weight for HA and HB. My big lambda is the central parameters, so the color of the representation. And U is a spin irreducible representation of W. The second part of the result is using what I presented, the factorization and the relation we can have, milking the algebra, we can say. Maybe it's not a good image, but okay, what we can find, we can say any tuples, lambda A, lambda B, big lambda, and U, that respects certain type of equation will give rise to a finite-dimensional irreducible representation. And then the other way we already present. There's some things I left behind on purpose. So I did all this for generic kappa. If you have a certain problem on kappas, if you have certain specific values of kappas, things can get messy. It's not. Otherwise, I spoke briefly about double coverings and spin representations, just to say you can, and we have done, to be precise, study the irreducible representation of W tilde, but this needs, it's an appendix, you need to do it, and you have information on the representations. They are quite interesting. You have to have information. The precise system of equations, I didn't present it to you. It takes plenty of slides, but it still has to be put in the clear way to see how small could we make it. Dimension of the weight space, I said it was one dimensional. I didn't prove it for you, but it is also linked with kappa. So if kappa is different, some bad things can happen. I will just think the last slides maybe explain a little more details. What happens? I will start here. So what happens when kappa is exotic, so non-generic? Some of those, when I speak of HA weights, I'm a bit cheating. So I presented as natural numbers, but in fact, this is generally not the case. They are a sum of kappa, sum of kappa plus certain natural number. So when kappa is negative and when kappa is a certain value, it may be that the weight space gets smashed together, and then you don't have one dimensionality, you don't have the same structure, representation will get messed up together. This is something interesting, but still something we need to look at. The last thing we want to do in the future is, I presented for you the 4D case because it's the first case that I can present with image, but it's also more interesting than that. It's with the result that Roy proved last year, that this algebra of symmetries is generated by the 2-index symmetries and the 3-index symmetries. We hope, but still need to prove this actual argument, that stacking dihedrals, so a direct sum of dihedral groups and Z2, we can do it using only what we've done in 3D with the dihedral and Z2, and what we will do in 4D, what we are doing in 4D with 2 dihedral. This is our hope for the future, and I think on this, I will welcome questions.
Very much. You started late, so we have a little time for questions. Are there any?
Actually, I think that this is certainly part of the critical aspects, but if you could go back to the diagram that we
This one?
Yes.
Yeah.
So I see a very visible here symmetry between the northeast, southwest, and diagonally.
Yeah.
Is that supposed to manifest something that you could have possibly understood?
This symmetry comes from the relation between tau and HA and sigma and HB. So sigma flip HA and tau, the commutation relation with sigma and HA is sigma HA equal minus HA sigma. So because HA are diagonal vector, if I on T, my triangular subalgebra, I have this eigenbasis of they are all a rank of weights. Flipping means I'm still isolated and I need to have this flipping. I need to have this this symmetry because I have some minus, except if say the weight have weight 0, where
Are you referring to the flipping for reflection by the other
oh
thing? Because the symmetry that I was alluding to was like the one that I see from the northeast and south.
okay, yes. Sorry, I misunderstood the north and the east. But yes, the symmetry on the northeast, in fact, can be seen. So if you flip with tau and then with sigma, you go here. And the reason the color are the same is in the central elements. The central elements as the same as a form that is maybe 1, 2, 3, 4. So tau bar 1, 2, 3, 4 is minus, and same with sigma. Up. So if you flipping those two gives the same. Yeah. So teal is plus, purple is minus, and
I might have myself one or two questions. If I understand, you use a model that has the algebra you like to study the representations of. What is the advantage of using the Dirac Dunkl equation? How would it have gone if you'd used the Laplace Dunkl equation?
The Laplace is the harmonic case and has been more or less more studied. I think it goes to the, if I'm not mistaken, to the Raka algebra for a certain group for the Z2. The main difference in my case is the main difference. One of the difference is that you will get on your group, you get this spin, you get the spin representation instead of the projective representation instead of the normal representation. The action of the group is a bit more complex. And then you have
with the spin, right? It's like because with your kappa equal to 0, the Dirac equation and the Laplace equation, they have the same conformal symmetry up to these.
Yeah, because in this symmetry algebra, the way we define it, if you put kappa to 0, you still have the smash product with the group.
My second question is, any connections with special functions?
Yes. The talk was a bit too long, but I wanted to speak about special functions. Another reason why this is interesting, and maybe the main reason why Dunkl introduced those Dunkl operators, in my point of view, was to define some special function. And indeed, say for the Z2n case, you get the Jacobi polynomials as an example. If you look at the representation as the polynomial null solutions of your Dirac equations. For one dihedral, you also get, I do expect that for x of dihedral, you will get nice special functions. And I think it would be possible to make it, to have an explicit form. But
any further questions? Thank you very much.